Good. How about now? Okay, great. So welcome to the class. We should be online. Sorry, I forgot the microphone. We are talking about cascades. Last lecture we talked about decision-based models of cascades. Today I want to talk about probabilistic models of cascades. And this will be very nice because this will then nicely fit into what we are going to do on Thursday and then next week, which will be about what we call influence maximization, where the idea is which nodes in the network do you want to target, who do you want to give free product to, or who do you want to infect so that the disease or the adoption of your product spreads as far as possible. And this goes by the name of Kate Middleton effect. I'll talk about that on Thursday. You will learn all about Kate Middleton. Okay, great. So probabilistic models. So what we talked last time was we talked about decision-based models where we think of nodes as being part of the network, and we think of them as deciding very kind of consciously, rationally about what, based on the payoffs, whether to adopt a given behavior or not. What we are going to do today is work on a different type of models where we will talk about not about decision making, but it's more like of the process of epidemic spreading, where the question is that basically we have this contagion that is spreading, and contagion in some sense is unobservable, but in some cases basically we will model it as some kind of random process spreading over the network. A good example of these types of things are diseases. Viral cascades in online media, in social media, and so on. So that's essentially what we will be thinking about. And then we will have this notion of virality, right, where basically we will think that a given, let's say, disease starts with a given node, a given patient in the network, and then this process will spread. And we'll be interested in knowing, right, does this process, could it run indefinitely long, or perhaps we have a disease that is not really contagious, so it will spread a bit and then kind of die out, right? That's kind of one of the main questions we'll be looking at. So what I want to do right now is do a quick mathematical derivation that will give us a sufficient condition when the epidemic will run forever versus when the epidemic will die out. Okay, that's the main question. And the way we will think of this is we'll analyze a mathematically very simple model of probabilistic contagion, and we'll analyze it on a simple model of the network, which means this kind of infinite tree where every node has d children. Okay, so every node d has d subtrees. Okay, so this will be a branching process. It will be like, you can think of it as an infinite tree where every patient, let's say, meets d people, and with probability q, the patient infects one of these d people. Okay? So the question is, for which values of d and q does this epidemic run forever? Okay? So rather than thinking of this on a network, we think of this as a kind of infinite tree where every node gets a chance to infect the other nodes, and then if the infection happens, it happens with probability q, then the downstream nodes, the children, again, each one gets a chance to infect the other people. Yes?
Is this assuming it can be reinfected?
No, it's an infinite tree.
I see.
Right? It's really an infinite tree where every parent gets to infect the children, and children has kind of have nothing in common. Right? So that's kind of the stylized mathematical model of this. I agree, it's kind of very simple, very stylized, but it's still useful. What do we want to compute? We want to say the epidemic will run forever if the probability that we will have at least one node at depth h that is infected as h goes to infinity, if this probability is non-zero, then the epidemic runs forever. And if the epidemic dies out, then it means that as the depth of the tree goes to infinity, the probability that we have an infected node at some level h goes to 0 or equals to 0. Okay? So if the epidemic will run forever, then the probability of having an infected node at any arbitrary depth, as depth goes to infinity, will be greater than 0. This means the epidemic runs. And if the epidemic dies out, this means that at some point the probability of seeing an infected node from some point on will basically be 0. Okay? Yes? Makes sense? Yes, makes sense. Okay, super. So let's try to derive this. So we say the P of h is the probability that a node at depth h is infected. And what we want to compute is we want to compute this limit here, whether this limit, whether what happens this P of h as h goes to infinity, and this P of h will have it's a function of two things, of Q and D. D is the fan out, Q is the infectiousness of the disease. Right? And we are reasoning about this behavior from the root of the tree. Right? Right? And the observation is that the root is the patient 0. So this guy is infected. And if we are able to analyze what happens from here to here, then essentially we have the identical problem here as well. Right? Now I have an infected root that infects its children. Exactly the same instance of this problem. So it kind of replicates multiple times. So all we need to reason about is what happens from here to here. Okay? That's the first thing. Now what we really want to do is we need to say what happens to this pH, and how does this pH change from h minus 1 to h. And pH is the probability that there is at least one infected node at a given depth. Right? So if this is the probability that the parent is infected, then, or probability that on the upper level, probability that on the upper level there is at least one infected node, then what we are doing here is to saying 1 minus q times p of h is the probability that no infected node that we see no infected node at depth h from the root. So 1 minus that is the probability that we will have an infected node at level h. What am I doing here? This is the probability the parent is infected, the transmission. This is now that this is the transmission probability. 1 minus that is that there is no transmission, and I want no transmission over all the D children, right? And 1 minus that is the probability that at least one of the transmissions will succeed, right? So that's how I connect the probability from the parent to the probability to the next level. Okay, so that's now we have a recurrence relationship that links h minus 1 to h. Okay, so now what is this limit of p of h as h goes to infinity? It's a result of us iterating this equation, right? Where f of x, which is h, right? F of x, p of h is whatever I had at the previous level times q, 1 minus that, raised to the power d minus 1, and I'm essentially iterating this equation. And what I mean by iterating is I start with f of probability that there is an infected guy at level 1 is 1. So I evaluate f at 1. I get a new x, I evaluate the new x, I get x2, I evaluate new x, I take this x2, evaluate function, I get x3, and so on. So that's what I'm iterating, right? Because I go from level 1, this is probability of having an infected node at level 1. This is now probability in some sense of getting an infected node at level 2, level 3, level 4, and so on. Or level 0, level 1, level 2, level 3. Okay? Clear what I mean by iterating? Right? I'm just kind of unrolling this iteration by basically writing it as f of x, and then I start with x equals 1, which means with probability 1 there is an infected node at the root. Now I get at the depth 0, I get the probability that there is an infected node at depth 1. I evaluate it at depth 1 to get the probability at depth 2. I evaluate at the depth 2 to get depth 3, and so on. Okay, that's what I mean by that. Okay, and as I said, we start with x equals 1 because the probability that there is an infected node at the root equals 1, right? There is a patient 0. There has to be a patient 0. So the way we can think of this is the following. I can think that here I have x, and here I have f of x. Okay, and what I'll be interested in is what is the fixed point of this process, right? Because I will be iterating this f of x thing, and I will first ask what is f of 1, right? So I will first say, what is f of 1? And then I will be iterating this. And let me show you what I mean by that. Let's assume that our function f has this type of shape, just for the purpose of the lecture. Assume this has this type of shape. So how will this iteration look like, right? It will basically start, I will evaluate at f of 1, and I will get some value, x, right? Here it is, right? This is now f of x here. Now I will take this f of x here, and I will reevaluate it, right? I will reevaluate my f, and I will get another x. And now I'll reevaluate f at my other x, and I will be kind of dropping down until I get stuck. And here is where I'll get stuck, right? Here, f of x equals x. So it means my iteration will get stuck, right? F of x I will be equal to f of x plus I plus 1, right? So I know where to start at x equals 1, and then you can think I'm like going down this staircase until I hit x equals y, okay? At least intuitively. So this means that this is a fixed point, right? This means that the probability that there is an infected node at some depth h will be constant, right? Because f of x equals x, right? This is x equals y. So it will kind of get stuck there, and I'll have the constant probability of having an infected node from some depth on. So now what we really want to do, right? So if I want the epidemic to die out, then I want this curve to be below this line. Because as soon as I cross the x equals y, I get stuck. Right? I get trapped in this kind of infinite loop, f of x equals x. Right? I'm just like iterating, right? So I want this entire curve to be below here so that I'll get stuck at 0, 0, which means the probability of having an infected node at a given depth will be 0. So I want this pink curve to be below x equals y. You guys should probably ask me a question. Does that make sense? Yes? Go ahead, yes.
So when you kind of iterate on f of x, are you traveling along that red line as opposed to like the real like line?
Yes, I'm traveling in some sense along this line, right? But I'll stop traveling when I cross the x equals y, because this is where I'll be stuck, right? My iteration will be stuck here if f of x equals x, right? I won't be moving anymore, right? So as soon as I cross this x equals y, I get stuck, and the probability of having an infected node at a given depth will be constant from then on as I keep iterating. Good question. Anyone else? Yes.
So f has to be monotonic, or in some sense.
Great, super question. So what you said, f has to be monotonic. So what we'll do next is we'll start reasoning about how does this curve really look like, and what condition do we need for it to be below this line. That's a good, thank you. Anything else? All right, good. So moving on, right? So what we want is that this f of x is below this diagonal line y equals x. So now the question is, let's figure out what is the shape of this function, of our function, right? I just drew this to kind of give you the intuition. So here is what we know, right? Our f of x is that function up there, right? I already wrote it out. It's up in the title in the black background, right? So what do we know? We know that f of 0, if I enter 0, I get 1 to the d minus 1, so that is 0. So I know f of 0 is 0. So I know this point. This is 0, 0. It's useful. The other thing is, what is f of 1? If I ask f of 1 is 1 minus q raised to the power d. Q is between 0 and 1, so this will be non-negative raised to the, so this will be somewhere between 0 and 1. A number raised to the number between 0 and 1 raised to an integer d will be still between 0 and 1. So 1 minus something between 0 and 1 is less than 1. So this function f of 1 will be less than 1 for any value of q and d. Okay, because q is a probability and d is the number of children, so it's an integer. Okay, so now what I established this point, and I established that point, the value at x equals 1. Okay, so we know two things. We know the curve starts under the diagonal, and I know it ends at 0, 0. Now I have two more things. First is I compute the derivative. And here is the shape of the derivative. And then I can evaluate the derivative at 0, which is q times d, which means is positive. So the derivative at 0 is positive. So what this tells me? The first thing it tells me is that my function is non-increasing and that it's monotone. The reason why it is monotone is because of the fact that if a derivative of a function is greater than 0 for across its domain, then that function is monotone, right? In our case, x is greater or equal to 0. X and q are between 0 and 1 because they're probabilities. D is greater than 1. So if we look at this this product will be less than 1. Raised to the power d will be, again, this will be something that is non-negative. This is positive, so this thing will always be positive, right? So the derivative will be positive all the time, which means our function is monotone, right? And then the other thing is, the other thing to notice is our derivative is non-increasing, right? What this means is that essentially our function will look like this, right? It will be monotonely, it will be decreasing in a monotone way. And it will be falling down at an increasing gradient. You can think of it that way. So now, what do I have to do? All I have to figure out is to say, how do I make this go below here? And because I know that at 0, 0 is the point of the highest gradient, I have to make this gradient to be below the line. If here at the beginning I'm below the line, I'll always stay below the line, right? I will never increase up based on the analysis here, right? So what does this mean? This means that this f derivative is monotone and non-increasing on 0, 1. Okay? So now we are kind of ready to learn to make our class, right? So if our f of x would look like this, then right, this is how my iteration would look like, and I would kind of slowly get to 0. Okay? So as I said before, what we require is for this function to be always below the diagonal, right? So for the epidemic to die out, f of x has to be below y equals x, right? Has to be below this diagonal line. So what this means is that derivative at 0 has to be less than 1, right? Because if derivative at this line has derivative 1, so if my derivative is more than 1, I'm basically getting above it. So the only way to stay below the line is that here I have the derivative that is less than 1. And then, as we said, because this function is non-increasing, the derivative will only get smaller, right? I'm only kind of turning, I'm not turning up. I'm only kind of turning horizontally, right? So what do I require? I require the derivative evaluated at point 0 is less than 1. What's the derivative evaluated at point 0? If I go back, this is f of x. If I evaluate it at point 0, at x equals 0, so this will be 0. It's 1 raised to some power, so this is 1. So it's q times d, right? So what do I require? I require that q times d is less than 1. Okay. So if q times d is less than 1, then this p of h will go to 0 as h goes to infinity. Okay? So now you are like, okay, you derive this q times d. What does this mean? Actually, this is a very intuitive and simple result, right? This is the number of children. This is the probability that you will infect a child. And this number is, q times d is the expected number of people that get infected by an infected person. And this is a super fundamental quantity of all diseases. It's called R0. And it's called, this is the reproductive number of a disease, right? So essentially, there is epidemic if the reproductive number is greater or equal to 1, right? So if in expectation, every patient infects at least one other person, then this will keep going forever, right? If an expectation, every infected person infects less than one person, then this will die out. Okay, so that's the bottom line of what we derived. What we derived is this concept of a reproductive number, which basically will determine whether a given disease will spread or die out. The disease will keep spreading if the reproductive number of disease is greater or equal to 1, and the disease will die out is if the R0 is less than 1. And this is really what people in epidemiology really care about, is this one single number which is called R0. So I will now tell you a few R0s for different diseases. For example, HIV has R0 between 2 and 5. Measles has R0 between 12 and 18. Right? So on average, somebody with measles will infect between 12 and 18 others. Ebola has R0 between 1.5 and 2. You guys may remember the news about Ebola. Actually, what is interesting about Ebola is that Ebola is so contagious that the only reason why the reproductive, why R0 is so low is because it kills the host too quickly. Right, so it's kind of scary, but this is kind of low, right? It's almost 1. But the only reason this is so low is because this is so bad that these people don't have a chance for the epidemic to spread, right? So that's one thing you learn. The other thing you learn is how would you prevent epidemics, right? This Q and D help you. Your goal, if you are a public health official, is to decrease R0. How do you decrease R0? Is by either decreasing Q or decreasing D. So you can quarantine people and say, hey, stay at home, and you are decreasing D because you limit human contact, right? So that's the way to decrease that. Or you can, for example, say, you guys wash hands, cover your mouth, and now you are decreasing the transmission probability, Q.
Given ranges, is that just to account for the differences in highly populated versus sparsely populated areas?
Yeah, it's a good question. Why did I I gave you quite wide ranges. The reason, of course, I gave you this is because there is this kind of notion of biological R0 in some sense. But then, of course, this is real life in different population densities with different cultures, different socioeconomic statuses, different countries, and so on. So there is quite a bit of variability, also kind of geographic variability of different countries. But I'll show you some example later, but the best, what people who are now trying to use massive amounts of data to simulate disease, what they find is that basically airports are the best way to spread the disease, right? If you think about it, planes, they're just kind of taking contaminated people from one airport to another, right? So it's the best way to spread, right? So it's a great way to spread the disease very, very quickly, very far, right? But yeah, these are quite wide. They're just kind of empirical, and then it depends on many other factors than just biology of the disease. So I wanted to give you this because you can now start asking similar questions about this. What would the R0 be if you look at social cascades in social media? And I will show you just one case study where there is a image sharing website called Flickr that lots of professional photographers use. And users can follow each other using the friend links, and they can like or favorite a photo. And what these people were looking was how this photo liking is spreading throughout the network of 2 million people, where you have 34 million likes and about 11 million photos. And the way the cascading process now of liking photos look like is the following, right? The question is, did a particular like, favorite, a heart, spread through the social link? And the idea is that if a previous user likes a photo and none of its friends have previously liked the photo, then this was not social contagion. But if I like the photo that one of my friends has already liked it, then it's probably in my feed because one of the friends has liked it. So you could say, aha, there was a social cascade. So that's how these guys kind of reverse engineer what the social cascades are, by basically saying, did you like a photo that one of your friends has already liked before? And you can kind of work backwards and figure out what is the social cascade. Okay, that's the data. Right. So for example, if you see that B liked the photo after A and E liked the photo after C, who liked it after D, and these guys are all friends, then you could compose a cascade like that. Right? And maybe these are some other friends who did not like the photo, so they did not get infected by this beautiful photo. Okay, that's essentially the idea. How can you now measure R0 for each of these, let's say, viral photos? There are two ways. One way is to simply say, let me estimate this Q times D as we discussed. So basically, given an infected node, let's count the proportion of its neighbors that have were subsequently infected by this photo, that have liked it, and let's average that. And here, for the reasons of skewed degree distributions, which is, think of the first two lectures, you also need to include this correction factor. But for us, let's just think about this. It's Q times D. And another way to estimate this R0 is to do it empirically, where you could say, given a starting node of a cascade, count the fraction of directly infected nodes and proclaim that to be R0. Right? So you could just say, patient 0, what is the number of infected nodes? That's my estimate of R0 versus I see the entire cascade, and out of that I computed this. And the question is, how good is this empirical estimate at the root? How close is it to the overall estimate? So every dot here is a different image, a different cascade. Here is the empirical reproduction number. Here is the estimated from the entire cascade. And what you see is actually quite good correlation, then kind of slightly drops off. Why is this interesting? This is interesting because it says that if you just look at the parent and you see what fraction of parents children get infected, that already gives you quite accurate estimate of what overall a reproductive number will be. So basically, even though social networks are very heterogeneous, even just knowing what happens at the first step of propagation gives you relatively accurate estimate of what happens through all the subsequent steps of propagation. And you see where this doesn't work well is really here, where these reproductive numbers are kind of crazy high. Right? Where basically you could have a big celebrity who has who a lot of people like, and then from then on, kind of the thing does not spread too long, and basically it kind of dies out. Right? This is below the diagonal. Right? So if it would be above the diagonal, it would mean in the first hop it spread just a bit, but then it increased its R0, and these things are below the diagonal, which means in the first hop it spread a lot, and then in the subsequent hops it spread somewhat less. So it kind of didn't have enough stamina to push through. Right? So this is an example of how to think about this reproductive number R0. Right? And what do you also notice, right, is that the reproductive number here, it's kind of quite crazy high in some cases. Right? And then you can say, why do these epidemics stop? Why don't they just go through the entire network? The reason for that is because the reproductive number is not homogeneous, and it changes over time as the news gets stale. So it's harder and harder for the information to kind of keep pushing. Right? So that's one of the explanations why this is happening. Right? And as I said, it's much higher than measles. Right, which also indicates that online social networks are quite efficient at transmission of media and information through its structure. That is also very interesting to think about in terms of, let's say, what's happening with Facebook these days. Okay, so this is what I wanted to say about R0. Any questions? Yes, Daniel.
Also, more that there's, let's say, certain types of nodes that are more likely to spread the information. Let's say political news, they're much more likely to spread in the corresponding echo chambers, right?
Oh, great question. So the question is, could you kind of make these models more interesting? So you could make them more interesting by for example, doing this per different topics. You could do this to also try to estimate R0 or influence of different nodes. The other thing that happens in social media that's important is that sometimes information spreads through social influence, and sometimes it looks like it's spreading, but it's really put on from the top, right? So imagine you look at the crowd of people and they start putting up umbrellas. You could say, oh, this is a social fad, right? Somebody put up an umbrella and now everyone says, oh, that's a good idea, I will copy you, I'll put on an umbrella, right? So you say the use of umbrella is socially spreading, but there could be just that it started raining and everyone's putting up umbrellas. And it will seem to you like it's spreading through the network, but really there was some external effect where people put up umbrellas, right? So that's confounding as well, and there are very good models to separate these things out. Yes?
For the way that they model spread, like in the very beginning, there's always the most recent last person you're friends that gives you the node. Is there any difference between doing that and having like a DAG of everyone in your social network that has given you influence?
That's a great question. So what you are asking is, right now here it was, the assumption was it was the last guy, I think the last guy who did it. Of course, the reality might be that you have seen 3 other guys do it, and then the 4th guy flipped you over. I will give you examples of that as well. So there is this notion of exposure and infection. And you could have, and then you can define what is called an exposure curve that says, what is your probability of infection with the number of exposures? And that doesn't have to be constant. It can be increasing, it can be decreasing, because you say, after I've seen some silly thing 10 times, I'm like, I don't want to see it anymore, right? So that's a great point. I'll give you some examples of that as well. All right, good. Thank you for the questions. This is awesome. So now I want to tell you about general epidemic models, kind of generalize what we talked about. And the idea will be the following, is that we are really thinking of virus propagation, flu, measles, things like that. And the way we think of this is that we have nodes on the network, and nodes can be in different states. Maybe green is healthy and red is infected. And we will have, let's say, different types of parameters. At least we need 2 types of parameters. This will be like flu type model, because we need parameter beta, which is virus birth rate. So that's essentially infectiousness of the virus. And we also need the parameter delta, which is virus death rate, which is the probability that an infected node heals. Think of flu, right? You can get a flu with a given probability, and then you get cured from flu with a different probability. Okay? And then, you were infected, and now you are cured, and you are here again to be infected again. Okay? And the way this will work is that there is this class of models that will be named by different letters, and basically this class of models tells you what are the stages through which the node can go. S usually means susceptible, so susceptible to the disease. Then the state of the node can move to what is called exposed, right? So this is kind of incubation period. From the incubation period, you can exit and not get infected, or you get infected. Now that you are infected, you can again exit the system, or you can get recovered or removed. And Z here is immune, right? A susceptible node can either be exposed and infected, or it can be immune, so it doesn't really matter what happens, and could then go to the recovered state, right? And now, given the disease, these boxes and these states, this state diagram will be composed in a different way. So let me first tell you about the first model, which we will call SIR model. SIR because it's susceptible, infected, recovered. And the node goes through these phases. And this would be a model of chickenpox or plague. Right? In chickenpox, you get the chickenpox and you can never have it again. Or in the terms, in the case of plague, that recovered, you can think of removed, which means dead. Okay? But you get the idea, right? Like you cannot be susceptible again. Right? So once you heal, you can never get infected again. Okay? That's the idea. So these are the models people work with, and generally they assume what is called perfect mixing, which essentially means that the network is a complete graph, or the network is a random graph. And then what you can do is you can write out the dynamics of this model in terms of differential equations, right? And you can say at what rate is the number of susceptible people changing. It is changing at the rate beta, which means susceptible people can be infected by the infected people. Then you say, aha, the infected people, how is their rate changing? The infected people, their rate is increasing because the susceptible people can get infected with the rate beta, but then the infected people are also getting cured or recovered by the rate delta, which is here I have how are the recovered people. They are growing with the rate delta because these infected guys can become cured. Yes.
Why do these depend on the network leak?
Why this? The reasons why usually people ignore the network and say that they assume perfect mixing is because now these equations are easy to solve. Right? Like, for example, here I multiply these two populations because anyone who's susceptible can get infected by the infected person. So I can just multiply here. Otherwise, I would have to consider how the network looks like here. And I'll give you later a result that kind of captures the entire structure of the network in one number. But generally, math is easier if you assume anyone links to anyone. That's really the reason. Okay? So this is the SIR model. And what is interesting, right, if you simulate it, here is the simulation, right? This is time. This is the number of susceptible, number of infected, and number of recovered. And if you simulate this model, what you see is, for example, at the start, everyone's susceptible. The number of susceptible people is decreasing. The number of infected people is increasing over time, reaches some plateau, but then starts decreasing because the population of susceptible people goes to 0. And then the people who kind of recovered goes back to 1, right? So this is kind of a typical way how an epidemic goes through a population, right? Like, for example, chickenpox would be an example of this, right? Where basically you have a lot of susceptible people and there's less and less and less. The number of infected grows, but then the number of people that can be, the number of susceptible people is lower and lower, so this has to go down as well, while the total number of recovered goes all the way up. So this is a model where kind of you have this one swipe of the epidemic throughout the population. There is a separate, different model that's called the SIS model, and this is a susceptible, infected, susceptible type model. And the idea here is that cured or healed nodes immediately become susceptible. So think of this as flu, right? You get the flu, you are sick for some time, and then you get healthy, and you can get another flu. So the node transition diagram here is that there are two states, susceptible and infected or infective. Susceptible people can become infective infected by the neighbor with some probability beta. And the infected people can get cured with probability delta, right? So simple two-state diagram. What is interesting is if you look at this model, then here are the transitions, right? This is the change in the number of susceptible people. You have two factors. One is that infected people are getting healed. So this means that the number of susceptible people will increase. But susceptible people can get in contact with the infected people, and with that rate, the number of susceptible people is decreasing. And then the number of infected people, it's kind of the opposite. The number of infected people grows with beta S, where S is susceptible, minus the infected people who get cured at rate delta. Right? And here I'm multiplying because I'm assuming that in some sense any susceptible is linked to any infected. So here is almost like a complete bipartite graph. So anyone can infect anyone. That's why I'm multiplying these two numbers here. And if you simulate this model, what is interesting is that you see here is that the virus can kind of linger in the network, right? There can be a case where there is a kind of a fixed fraction of people is infected and some fixed fraction of people is healed, right? Because some people are infected, some people got healed, the virus moves over them. At this time, some infected people got healed, and kind of the virus never takes over and the virus never dies, right? It's kind of at this intermediate level, right? So what we are really interested about is this notion of epidemic threshold, kind of an equivalent of R0, that will say, given this virus strength, beta over delta, which beta is the infectiousness and delta is the healing rate, then if this is, let's say, below some epidemic threshold tau, then the epidemic will eventually die out, right? And the question is, for a given graph, what is this epidemic threshold? Okay? This goes to your question. You're asking me about the network. Right now I'm saying I have beta, I have delta, I have the graph. What should beta over delta be? What should this epidemic threshold be for the epidemic to die out? So what is tau? That's the question. I won't go through the derivation. I'll just give you the result. But there's an elegant result that says that the epidemic will die out if beta over delta is less than tau, where tau is 1 over the largest eigenvalue of graph adjacency matrix. Right? So basically, eigenvalues of the graph adjacency matrix, which we have already kind of talked about with spectral clustering and PageRank, are extremely informative to describe the structure of the graph. And here, all we care about is the largest eigenvalue of the adjacency matrix of the graph. And if beta over delta is less than 1 over the largest eigenvalue, then the virus will die out. Otherwise, the virus will survive. Let me show you this with a simulation. Here is a graph on 10,000 nodes and 30,000 edges, where we are simulating the SIS model. This is at the first iteration, and then we kind of keep iterating it over time. We are fixing beta to be the fixed number, and then we are changing delta so that beta over delta has different values. Beta is 0.001, and delta is 0.05, 0.06, 0.07. The x-axis is time, the y-axis is number of infected nodes. And then here I show you betas that have different threshold values. So this is above the threshold. So here the virus survives indefinitely, right? The number of infected people does not go to 0. The blue line is beta over delta that's below the threshold. So this is now below 1 over the largest eigenvalue. And you see how the number of infected people kind of goes to 0 very quickly, and here it dies out. And then the green one is when beta over delta is right at the threshold. And then what happens right at the threshold, kind of, it's very hard to say, but essentially what you see is that this virus kind of keeps lingering and dying, but never really dies, right? So if you are right at the threshold. But if you are above, the virus survives. If you are below, the virus dies out. And of course you can ask, does it matter how many people are initially infected and things like that? And here is what I'm trying to show you. So this is the number of initial people that are infected. And if you are below the threshold, it doesn't really matter. It goes to 0. Here is when you are at the threshold. You see it's kind of going to 0, but it's still not 0. Like it kind of slowly survives, slowly going to 0, but never really dies out. And here is when you are above the threshold, let's say when you are at 1.1, regardless with how many people infected you start, it kind of gets, the virus survives in the network, right? It doesn't really matter. There is this kind of steady population of infected people to which it converges. Okay? So this is what I wanted to show about these SIR and SIS type models. And of course, as I mentioned before, you can make them much more complicated. This is going back to this example of Ebola. This is the type of network that they were modeling about the spread of Ebola. And it's all about the planes and the airlines, as I was saying before. And then as I try to indicate, these models can get more and more complex. So I think this is the model for Ebola, that it goes from susceptible, is exposed, I is infectious, H is hospitalized, F is dead but not yet buried, and R is individuals kind of no longer transmitting the disease, which either means cured or kind of underground away from people, right? But you can see essentially how this model has these different states, and then the way you model the epidemic is to estimate these parameters that basically tell you how these transitions happen, right? How does a patient move from one state to another, right? So here the interesting thing is once you are infectious, people can be hospitalized, and then from hospitalized, essentially because there was no cure at that point in time, people would die. Either people who are infectious would die immediately or would go to hospital and then die. And then they also labeled this process, which is from death to the burial, right? And all I try to show here is that depending on the disease, this transition diagram might be different. You can write out the differential equations as I saw, and then the question is how do you set these parameters, betas, deltas, alphas, to capture the overall population dynamics. And if you feed this on historic data, here is an example how predictions were being made, right? So this is this is time versus the number of deaths. The red is the observed data. And then the lines here are different runs of the model, and you see the projections of how many deaths there are projected in the next few days. And this was really done in real time when Ebola epidemic was spreading in Africa. And there is a very good paper that you can read about this estimation of R0 of Ebola, right? But you can see how these models are really used to make these types of predictions and inform our health policy. So, and as I mentioned, the R0 for Ebola was between 1.5 and 2 because of kind of the reasons I was saying, even though it's much more infectious than that. Okay, good. So this is what I wanted to do. Now I wanted to quickly show you one application of this that you could apply to rumors or fake news spreading in social networks. And let me show you the application of this, right? So what we talked so far, we had this notion of SIS type model where you have the infectiousness and the recovery. So in the way you could think of this in the context of Twitter, you could say you have susceptible user. These are Twitter accounts. A person is infected if they believe the news or they believe the rumor and maybe even retweet that thing. Exposed means you were exposed to the rumor or to the news, but you don't believe it yet. And Z are skeptics, which are basically people who don't contribute in spreading the news or rumors, right? And we would like to model the spread of basically cascades on Twitter network using this type of model. As I mentioned, we already talked about the SIS model. That's a model of influenza or common cold. And in our reasoning, we'll basically think about the individual either believes the rumor or the individual is susceptible to the rumor. We will expand this because we also need skeptics, which are people who are immune to the rumors, right? So our transition diagram will be like this, right? We have the susceptible population who can get exposed and then can be infected. Some people can be susceptible and get infected immediately, and then some people can be susceptible and kind of go this way to be exposed versus going to become skeptics, right? They were exposed, but they don't contribute. Notice here that we decided to parameterize this flow into E two ways. One is kind of going towards skeptic but become exposed, and the other one is going towards infected but be exposed and then become infected later. And there's also a direct path. So this is how we will model this thing, that we have the rates here and here, but then L fraction goes straight and 1 minus L goes up, And same here, the p fraction of beta guys goes straight, 1 minus p goes down, and then I have the row that goes from exposed to infected. Okay? And just as a case study of this model, what did they do? They took 8 different events from Twitter. Real events was Boston Marathon explosions, resignation of previous pope, some explosion in some oil plant in Venezuela, and something about Michelle Obama at Oscars. These are real events. Here are rumors or fake news. Fidel Castro, some shooting in Mexico, doomsday, and Obama getting some injury. And they were trying to analyze, basically collect data about retweets of 8 of these different stories, and then try to estimate the parameters of the model. So what they did was to say, let's have the number of tweets on a given topic over time as the number of infected people. I is the number of infected people based on our model, and then the researchers just use the grid search to find the parameters that give you the minimum error, right? So the idea is, we talked about the model, they selected the parameters, simulated the model, and so what's the error between the actual number of tweets and the predicted number of tweets by the model, and they would iterate this until this error was small over the grid search over the parameters. Okay? Is it clear what happened? Yes? Okay, first row is happy. How about the middle rows? Happy as well? Okay, great. So this is what they did. So let me show you. So this is data. This is time versus a number of tweets. Blue is real data, and red is the model. Here, what this is trying to show that the SIS model is not able to feed the data, while this SEIZ model is able to feed the data perfectly, right? So they said, how do I set parameters of the model so that the red curve feeds the blue one, and they would just do the grid search over the parameters and pick the best parameter set, right? So this is the first thing to see, is that basically they can model this thing amazingly well. Here's one case, here's another case for another story. Again, SIS model is not able to model this nicely. These guys are able to model it quite nicely. You see some error here, maybe a bit of an error there. Okay? So this is what is interesting. What is then also interesting is that these guys came to this notion of this metric that they call R sub SI. And you can think of it as some kind of flux ratio between people leaving people moving between exposed and infected, and then people moving into the exposed state, right? So what is this saying? This is saying this is beta times 1 minus p. So that's the number of people who are moving from S over the top arc into E. This thing here are the people who go from S over B and 1 minus L into E. So it's kind of the influx of people into E. And then this is the outflux of people. So people leaving E to go to infected, right? And they are interested in this ratio, right? So in some sense, this ratio is the speed at which people get infected versus, the speed at which people get exposed divided by the speed at which people get infected, get out of the exposed state. And what is interesting, if you plot their data, they find that for real events, here they are, this ratio is much higher than for fakes, right? So what does this mean? This means the following. It means that for real events, this ratio is greater than 1. So it means that the number of people who get to the exposed bucket is far greater than the number of people who are getting into the infected, who are kind of retweeting, right? While for fake news or for fake stories, they find this thing to be low. So this means that, if I go back, this means that this term, in some sense, is bigger than the above term, right? So it seems that kind of the story is so viral that the number of retweets is far, in some sense, bigger than the number of exposures, or the rate of retweeting is faster than the number of that exposures come, right? And this is kind of seen over and over again, that kind of fake news are engineered to be super viral, and they spread super quickly and get retweeted very quickly. Yes? Where you mean in my? Yes, this epsilon is just an error term that they were, I think, trying to estimate as yet another parameter to the model. Yeah. All right. Good. Yes.
Is there any intuition on why this Michelle Obama thing is so low?
I do, please read the paper.
It's like an outlier.
Yeah, it is a bit of an outlier. I agree. Those three, yeah, I agree. There is a lot of interesting observations here. Yes?
Is there any reason why there isn't an edge from E to Z, so that people who are exposed can like research and then become skeptics?
To go this way. That's a good question. I honestly don't know. So I would suggest checking the paper, seeing what they did. Maybe doing this thing would be interesting as well. I agree. It's a good question how many people research, but I guess more and more. So that's an interesting suggestion. I like it. Okay, good. So now the last thing for the last 20 minutes. I want to talk about a probabilistic model of cascades that is called independent cascade model, and this will be the model that we will be using for influence maximization on Thursday. Okay, so here's the idea. The idea is that in this model we were given the network, and the edges of the network have probabilities assigned to them. And the way you can think of this is that every edge has a probability, so this means that if node F gets infected, it will spread the disease this way with probability 0.4, so we'll flip a coin, and if the coin says yes, we spread to G, and here we'll again flip a different coin with a different bias and spread, and we'll flip another coin here to spread the disease, right? So the idea is that basically this is an independent cascade model because every transmission happens independently of all other transmissions, right? So the idea is that when a node becomes infected, we say then it activates each of its outgoing neighbors, outgoing links, with a probability that's assigned to that link, to that directed edge, right? So the way this would work is that then basically activations spread throughout the network, right? So the idea is that I have some patient 0 here, and then I would go and flip these 3 biased coins, and let's assume that one of these coins comes up heads, so that the infection spreads here. Now I have this guy, and this guy now flips 2 coins independently, each one with a different bias, right? The guy gets infected, flips the coins, and now if this coin says yes, the infection spreads here. Now this guy gets to flip 1, 2, 3 coins. We see what happens. This guy gets to flip 1 coin, see what happens, and if the disease stops spreading, this is what we generate, right? And we think of this as a cascade now that started at node A, went to E, and then went to E and F, and then stopped. Okay? And the reason why this is called independent cascade model is because we flipped each of these edges independently, right? And here it's interesting, right? So for example, if this edge would fire, this node would not get a second chance to transmit because it already got infected once. So you cannot get infected multiple times under this model. Okay? And this is a very simple model where you say, if I infect this node, how will the disease spread? And you can easily simulate this many different times. And every time you simulate it, the downward cascade, the tree, might be a bit different. Okay? So now the question is, with this independent cascade model, could you make this thing more realistic, right? So for example, what people have done is rather than saying, if I have a real network, how would I estimate all these infection probabilities over each edge? Maybe I would try to estimate them from data, and that's very hard. So what people sometimes do is to say, let's make all the edge weights to be the same. But this is kind of too simple, right? You want some heterogeneity over the edge weights, but you don't want all of them to be different, and you don't want all of them to be the same. So a good way how to make these models more realistic is the following, is that you separate out the notion of exposure with the notion of infection or adoption, right? And the idea is that exposure happens whenever one of your friends exposes you to the virus, to the piece of information. And after every exposure, there is some random process that determines whether you will adopt or activate or not, right? And now what is interesting is that we can start asking about the we can plot out the exposure curve, which is the probability of adopting new behavior as a function of the total number of friends who have already adopted the behavior, right? Or, you know, probability of you adopting as a function of number of exposures that you have received. And you could ask, what is the dependence, right? In the probabilistic spreading-like models, this dependence will have this type of shape, right? This is the number of friends that have adopted versus your probability of adoption. And if each one infects you independently with probability k, then this will have this type of shape, right? And then if cascades would be more of a decision-based, then this is how basically what we'd expect to happen. We'd expect to have this kind of step function, right? You'd say, I don't get infected until certain number of my friends get infected, and then I get infected with a very high probability. Okay, so this reminds of decision-based, and this is consistent with probabilistic spreading. Yes? 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 How about this side? Okay, great. Okay, so this is decision, this is probabilistic. And then what becomes interesting is that you can make these exposure curves even more interesting, right? You could have an exposure curve like this. And what this would mean is basically there is some optimal number of exposures when you are most likely to convert. And after that, you just stop paying attention, right? You know, you could imagine that in advertising, things like this might happen, right? This is like the probability of infection just increases with the number of exposures. Or you could have something where actually the first exposure is the most infectious, and then it decreases. And you can actually go and estimate exposure curves for different applications. So let me show you some estimates of these exposure curves. So here is one example. This is a real-world viral marketing campaign where basically people were able to buy products, and then they were able to recommend products to their friends. And if the friends would buy, the friend would get 10% discount, and the recommender would get 10% discount as well. So it was this kind of incentivized viral marketing. So you can ask, how does the probability of you buying a book change as more and more of your friends recommend you that same book, right? Right, and this is what would happen, right? And if you would get to buy books with discount, both of these people get excited and happy, right? And of course, then this person could further recommend the book to the grandma and so on, right? And this could spread. So the question is, how does your probability of buying change as more and more people recommend you the book? And what's interesting is if you look at the graph, this is how the graph looks like, right? So this is the number of recommendations people received versus probability of adoption. What do you notice? You notice two things. The first thing you notice that it has this kind of nice diminishing returns shape, right? You see it kind of saturates. Another thing you notice that the infection probabilities are very low, right? So even if you get this after 10 recommendations, your probability of buying is only about 5%, right? This is for buying DVDs, so movies, right? This is one example where basically this curve is very consistent with probabilistic contagion type model. Okay, so that's one example. Another example is you can look at people joining social groups online. This is from a social network called LiveJournal, where the way you can think of this is you have people, and every person can say how many friends are already members of a group. Will I decide to join the group? Right? So it's essentially how many people are part of a given discussion group. Will I join that discussion group? Right? So the question is, how does the probability of joining the group depend on the number of friends that are already in the group? And here's the result. And notice it's again this kind of diminishing returns. Here, you know, the probability is 1.5 to 2%, as more and more of your friends are members of that online discussion group. What is interesting here is you kind of notice this kink, right? So it seems that at least between 0 and 1, there is something, and then it kind of increases and becomes a diminishing return. So it's not clear, is this an S shape? Is this a threshold here? Or is it just diminishing returns all over? But it's interesting, between 0 and 1, the increase is smaller than from 1 to 2. Okay, so this is what I wanted to show you about how these exposure curves look like. So I want to finish the lecture with showing you some examples of how these exposure curves look like on Twitter, right? So here is analysis of 3 billion tweets and 60 million users, where what these guys were doing is they were measuring these exposure curves for top 500 most popular hashtags, right? So the idea is, how often did you see the hashtag versus what is your probability of using it, right? And then they were saying, how could I characterize or understand the shape of this curve, okay? And what they notice is that a typical pattern for these curves is that they kind of start, they increase quickly, reach some peak, and they kind of taper off. So what they did was the following. They characterized these curves according to what they called persistence and stickiness. Persistence, they said, is the ratio of area under the curve and the area of the rectangle that is kind of enclosing the curve. So the more persistent the curve it is, the less it will drop, right? And the less the curve drops, the bigger the area under the curve. So the bigger the ratio between the area under the curve and the area of the square. Okay, you guys see what I mean? Yeah. So it's basically area under the curve versus area of the entire square. If the curve is persistent, then it will stay flat. It means it will kind of cover most of the square. And then they said they also have this notion of stickiness, which is what is the highest value of p over any k. So basically, one is asking how quickly is the curve decaying, and the other one is asking what's the peak of the curve. Yes.
So this does not characterize. So in the red line, for example, it looks like it's decreasing.
Yeah.
Whereas in the above example, it's not clear it's decreasing. It looks like it may be consistent. So it does not characterize the trend.
Correct.
After the peak.
It does not characterize the trend, but what it characterizes is what's the maximum infectiousness, and then does this infectiousness stay flat, or does it somehow decrease in some way? Okay. So good observation. This is just one possible way to characterize things. Okay. So here is what they find. What they do is they also come up. So they put the hashtags in different groups. Political, music, ideology, technology, movies, sports, and so on. And they also for every group, they also come up a random null model. So x's are truth, and they also come up with the null model, which is basically what does the average over all the topics, what is, let's say, the average persistence across all the topics. And what they, for example, find is the following: is they find that idioms and music are less persistent than, let's say, a random set or an average hashtag. And they find that politics and sports are more persistent than random hashtags, right? What does this mean? This means that these things have a very quick decay, while politics and sports seem to be spreading much longer at a kind of persistent rate, right? So these two guys, they go up and then go down. These guys go up and basically remain flat or don't decrease too much. Okay, this is the persistence, which was the ratio. Wrong. Sorry. Okay. I wanted to show this. Sorry. Right. Persistence was this ratio in the area of under the curve versus the curve, and this politics and sports is persistent, music and idioms is not persistent. So that's one thing, one observation. And another observation is in terms of stickiness, which is the maximum infection probability. Here, for example, you notice that music is very infectious. So basically it's very event driven, right? It gets very quickly to high level of P and then decays quickly. You notice that, for example, technology and movies has low infectiousness, right? So it doesn't seem to be spreading so fast or with such a high rate than, for example, movies, right? So music, right? So music-related things, or I guess musician-related things, celebrity-related things, have a higher stickiness than a random set of hashtags, and technology and movies have lower stickiness than a random set of hashtags. Okay, so this is what I wanted to convey to you today. Is essentially what we talked about are these 3-4 different important concepts. One was this notion of a reproductive number. Then we talked about these general epidemic models like SIR, SIS, SEIZ. And then we talked about independent cascade model, application to rumor spreading. And then we also talked about this notion of the exposure curve and how does the number of exposures relate to probability of infection. And then we looked at the case study of application of this concept to Twitter to try to measure the exposure curves and characterize them. There's a lot of super cool research beyond this that has looked at spread of cascades over large social networks like Facebook. There is a super cool paper about how usage of LinkedIn spreads like a virus over the world, and how essentially it is important that when you are building products to have this virality component where your users can invite other users, and this way your product spreads. Examples of these are LinkedIn, Facebook, which are basically grew by other people inviting people to join the network. So we'll talk about on Thursday about how to select the optimal set of people to invite so that you get a big cascade going and you get this viral effect starting. Thank you very much. See you on Thursday.